Everyone. So if you haven't noticed already, your graded assignment 2s are at the front here. I thought we would start by so I believe that our midterm is scheduled for the 20th, which is our next class. Is that right? I heard that, is it true that you have a 301 midterm on the same day? Does that make you happy? No.
But that maybe doesn't make us happy in general.
Yeah, so it's going to be up to you. I'm not going to delay it a long time, but if you would prefer to write the midterm in this class on Wednesday next week, we can do that. But it's going to require more or less uniform agreement from the class. I'm not going to change what I scheduled if it's going to inconvenience a small number of people, even if most of the people want that change. So who would like to write the Phys 304 midterm on Wednesday next week? Okay. Who would like to write it on Monday? You look like
Sure.
Yeah.
We'll then move on. Okay.
So
22nd, then yes, that's.
the 22nd. Do you have something else going on Wednesday that is causing a problem?
Not the midterm, but
Yeah.
I have for the computer science class, the coding assignment and
An assignment?
take long stuff.
It's a long assignment.
Yeah.
Okay. Yeah. Okay. Well, let's see. I don't know how to do that. Let's think about it. I'll mull it over as we're going through this stuff. All right. Okay. So I haven't made any decisions on that. Let's get rid of, how can I go to full screen? Shoot. Yeah, okay, people can stop putting stuff in the chat. Thank you. I got your messages. Okay, perfect. So hopefully that will go to full screen. All right, so what I want to do today is I want to start chapter 3. Chapter 3 is called formalism. And so the idea is that we're actually not going to do a lot of new concepts in terms of how to, I don't know, find wave functions or things like that. What we are going to do is we're going to try to recast a lot of what we've already done in chapters 1 and 2 in some new notations. And what I'm going to try to do is I'm going to try to be pretty explicit about how we can make our calculations that we do in quantum mechanics parallel a lot of the techniques that are used in linear algebra. And so to start, as you've already seen, we do a lot of calculations of this style when we solve homework problems and things like that. So it's like the conjugate of a wave function times some other wave function, integrate overall space. Or if you're calculating expectation value, we'll put an operator in between the two functions in the integral and calculate expectation values in this way. So what I want to start with is just to give a name to this kind of calculation. So in particular, this first calculation is called an inner product. So this is an inner product between functions, say psi1 of x and psi2 of x. And so you may well have heard of this language in some other context, some other course. I'm just going to repeat it so that we're all on the same page. So inner products, I claim, generalize the idea of a dot product. Dot product between vectors to the domain of functions. In fact, what we'll see is actually, not only are we going to generalize the idea of a dot product, but our inner products will contain a little more information, more detailed information than a simple dot product. So inner products have their own kind of shorthand notation. So inner products have a shorthand notation. And we're going to start using that notation. It looks like the following. So we're going to say psi1, psi2 is defined to be this integral from minus infinity to plus infinity, or whatever your domain is for your function. So if this was like infinite square well, we might go from 0 to a or something like that. But then it's exactly what you think. It's the conjugate of psi1 times psi2, and then we integrate with respect to x. Okay, so how does this resemble the idea of a dot product? We're going to think of two different aspects to this. If we look at the full time-dependent Schrodinger equation, it has like an I h bar d by dt of psi. And so that complex I in front of that time derivative requires that our wave functions are complex numbers, complex functions. And so I want to see, what does it mean to take a psi1 star times psi2? So let's start there. So let's first consider a pair of complex numbers. Okay, so Z1 is going to be some magnitude times e to the j phi1, and Z2 is going to be its own magnitude, e to the j phi2. So if I was to think about taking Z1 star times Z2, so just like we were doing psi1 star times psi2, doing that kind of calculation. Well, it's going to be the product of magnitudes times e to the j. And let's see, it's going to be a product of exponentials. But remember, I have to take the conjugate of Z1. So Z1 star would be its magnitude times e to the minus j phi1. So I'm going to have a product of these exponentials, which I can write as an exponential of difference. So it's going to be phi2 minus phi1 times, well, that's it, in fact. Okay, if I was to define theta as the difference between phi1 and phi2, I could use Euler's equation to rewrite this complex exponential, and I could write it as Z1, Z2. Let's see, it would be cos theta plus j sine of theta. And so if I was to focus on, say, just the real part of Z1 star times Z2, well, that's going to be everything that doesn't multiply j. So it's going to be the product of magnitudes times cos theta. Okay, so it's Z1, Z2, cos theta. But this is very much like taking the dot product between a pair of vectors. If I have two vectors and I take their dot product, I could express that as the magnitude of V1 times the magnitude of V2 times cos theta. And so the real part of this product between Z1 conjugate and Z2 is like the dot product. What does the dot product tell us? It says if the angle between two vectors is 90 degrees, we'll get cosine of 90, which is 0. And so perpendicular vectors have 0 dot product. So if I was to look at Z1 star times Z2, and I found that the real part was vanishing, then I would say that those two complex numbers are perpendicular in the complex plane. So if the real part of z1 star z2 is equal to 0, then z1 is perpendicular to z2. So we could draw a picture of that. So I could draw some kind of complex plane. Here's my imaginary axis. Here's my real axis. And I can put some complex numbers in here. So maybe this is the point z1. So here's its length or its magnitude, and it makes angle phi1 with the real axis. So if I was to draw a z2 that was something like this, here would be my z2, this would be the magnitude of z2. Here would be phi2, like so. And so this one would have an approximately real part of the product of z1 star and z2 equal to 0, because I tried to draw these to be approximately perpendicular to one another. But this original product, it also has an imaginary component. And so let's look at the imaginary part of z1 star and z2. Well, it's right here. It's still going to be the product of magnitudes. But now, instead of cos theta, sorry, this should not be sine of phi, it should be sine of theta. Okay, so we get sine of theta like so. But what is, in terms of vectors, what is a magnitude of v1 times v2 times sine of theta? It's not the dot product, but cross product, that's right. We have to be a little careful because the cross product really results in a new vector. So I'm going to restrict ourselves to thinking about just the magnitude of the cross product. And so that's equal to v1, v2 times sine of theta. All right. So if my vectors are parallel or anti-parallel, so their angle is, say, 0 or pi radians, then the sign will vanish. And that would mean that if our imaginary component of z1 star times z2 is 0, that means our z1 and z2 are either parallel or anti-parallel in the complex plane. So if the imaginary part of z1 star z2 is equal to 0, then z1 is parallel to z2 or anti-parallel. Okay, and so we could draw that as well, but you could probably see what it's going to look like. So here's my real axis. I'll just make up some z1. Here's phi1. Here's the length of z1. And then maybe to avoid clutter, I'll make my z2 an anti-parallel vector. z2, here's the magnitude of z2. This is phi2. And maybe for completeness, I'll put in, here is theta. Approximately anti-parallel. All right, so when people say that, you'll often hear people say that the inner product is a generalization of a dot product. And so what they're really referring to is this kind of condition where the real part of this product of the complex functions vanishes, which would imply perpendicular vectors, or if you take the inner product of a complex number with itself, then it's by definition parallel, so the imaginary part will vanish, and we'll get just Z1 magnitude times Z2 magnitude, cos of 0. Cos of 0 is 1. And so you just get this square of the length of a vector. And so that's where the dot product analogy comes from. Okay, so what we can summarize then is that this product psi1 star times psi2 that we see so often, what it does is it encodes information about the dot product. And the dot product is telling us about the parallelness to make up a word. And it also encodes information about the cross product, which encodes information about how perpendicularness of psi1 and psi2. Okay, we're going to talk a lot about functions that are orthogonal to one another. So if two functions are orthogonal, we're going to say that they're in some sense perpendicular to one another. And so we're going to define what we mean by that in more detail right away. Or shortly, I should say. Okay. But another way to think of like a dot product, if I have two vectors represented in component form, if I take their dot product, what I do is I multiply their components and then add all those things up. So it's like x1, x2 plus y1, y2 plus y3, sorry, z1, z2, z2, and I add them up. So how can I see how the inner product is like that in a sense? So we can vectorize, to make up another word, vectorize a function via sampling. So, okay, let's see. I'm going to draw some kind of vertical axis and a horizontal axis. This is maybe my x-axis. And so I'm going to consider two functions. These functions are complex. And so what that means is I need to consider both their real and imaginary components. So this is going to be a busy little figure, but let's imagine I've got some function f of x, and I'm going to say, I'm going to write this as f sub x, and then I'm going to draw another dashed line type function, and I'll call this something like fy. And so what I'm going to do is I'm going to say my complex function f of x is equal to fx plus I fy. Okay. And so let's imagine that these functions live on some kind of domain. And so maybe the domain that I'm interested in is from A to B. Okay, so I'm going to draw some vertical lines at A and B. So to vectorize this function, what I'm going to do is I'm going to imagine taking some samples of these real and imaginary components. And so I'll do my sampling coarsely to begin with. And so this would be like fx1, this is fx2, this is fx3, and so on. And the same thing for the imaginary component. I sample it at the, I probably didn't draw it very well, but I'm supposed to be sampling at the same values of x. So I could do a bit better, probably, something like this. Okay, and so this is going to be like fy1, fy2, fy3, and so on. Okay, so if I want to consider something like the inner product between two functions, two complex functions, f and g, I have to draw another set of functions on here, and I have to have real and imaginary components. So I'm gonna, to be complete, I'm gonna do that. So here's my gx, the real part of g, and I'm gonna sample it at all the same values of x. I won't bother labeling them gx1 and so on, but that's what we would do. And then I'd have the imaginary components, and so maybe it's doing something funny. Here's gy, and I sample a bunch of values. So now I've got all these samples of the real and imaginary components of my two functions f and g. And so we could think about, like, what is this inner product actually doing? Well, f, g, it's an integral, but an integral is just a fancy way of doing like a continuous sum. So what I'm going to do is I'm going to break that down into a discrete sum, and then we'll generalize once we see how this is working. So this sum is like taking f1 star and multiplying it by g1. But f1 star would be like fx1 minus I times fy1, and g1 would be gx1 plus I gy1, and so on. Okay, and so that's the first term, and then we would have our second term, g2 plus, and so on, all the way up to fn star gn. Okay, so we could write that more compactly with a sum kind of notation. Sum from I equals 1 to n of f I star times g I. Now this is starting to look more like a dot product, where we think of our samples as components of a vector, if you like. And then we just multiply components and add them up. The wrinkle is that one of them is, we have to take the complex conjugate before we do the sum. All right. So to continue this kind of analogy with linear algebra, what we're going to do is we're going to consider G in our inner product notation as a column vector. As a column vector. And so what I mean by that is I'm going to write G as G1, G2, and so on, all the way to Gn. So it's an n component vector. Just so you have it in the back of your mind, what we're ultimately going to do is we're going to increase the density of our samples. So our vectors are going to get more and more and more components as we make our sampling more and more dense. And in the limit of continuous samples, our vector is going to have like a continuous range of components, if you like. Okay. And we're going to take G as a row vector. Sorry, we already did G. We have to do F now. F is a row vector. But what we have to do is we have to make sure we conjugate complex conjugates of the components of our F row vector. Okay, so there they are. And then if we were to do this inner product, between f and g, it's like multiplying these vectors. So we're going to have like an f1 star f2 star up to fn star. And then we got to multiply by our column, g1, g2, gn. So if we just do our matrix multiplication, it's first element times first element plus second element times second element, and so on, last element times last element. So it's going to be f1 star g1 plus f2 star g2 plus and so on plus fn star ga. And so that's exactly the definition that we wrote down earlier. Okay, the integral definition is just a continuous version of that. Okay, but we have a bit of a problem. This is an okay approximation to the inner product. However, to improve the approximation, we'd like to increase the density of samples. But let's think about what would happen if we did that. If I increase the density of samples, just n is going to grow. And so that means we're going to have more terms in our sum. Now, it could happen that for certain functions, all those terms come out to be positive. And if they're all positive and we keep increasing n, then the result of the sum is just going to keep growing as we change our density of samples. And that's not good. So we don't get a consistent answer, or we don't get an answer that let's see, asymptotically approaches a stable value as we increase the number of samples. That's a problem. So if we increase n, the number of terms in the sum grows, and our answer for this inner product does not converge to a stable value. So we need to fix that. And the way we're going to fix it is we're going to scale the sum by the spacing between our samples. So as we decrease the spacing, our scaling factor goes down in proportion to the number of terms that we add to our sum. Okay, so we're going to fix by multiplying by delta x is equal to b minus a over n. Let's see what that means. B minus a over n. So here, b minus a is the width of our domain. If we divide by n, the number of samples, what that's telling us is our delta x is right here. So if I increase n, delta x shrinks, and I get more terms in my sum, but our approximation to the inner product will converge to a stable value. Okay, so now we have our inner product is going to be approximately given by the sum from I equals 1 to n of fi conjugate times gi, and we're going to put in our little scaling factor there. And so now this is exactly the kind of Riemann sum that you're used to seeing in calculus. We take the limit that n goes to infinity or delta x goes to 0, and we can write this as our integral, and we recover the original definition of inner product. So we take the limit that n goes to infinity, which is equivalent to delta x goes to 0. And our inner product is, f star of x times g of x dx. So this is the inner product between f and g. All right, and so the important part of this, like we could have just written down, this inner product, but what I really want you to take away from this is how we've built this up from an analog to linear algebra, dot products and cross products and discretizing continuous functions and so on. So we say that f and g are orthogonal if this inner product is equal to 0. But this is actually a stronger statement than just saying something like a dot product is 0, because we're requiring, this is a complex valued function, has a real and imaginary component. We're requiring that the real part be 0. That's like the dot product vanishing, and the imaginary part has to go to 0 as well. That's like the magnitude of the cross product vanishing. Okay, so that's our definition of orthogonal functions. What we're ultimately going to think about doing is taking a set of mutually orthogonal functions and defining those to be a set of basis functions. Just like for a vector, I could write any vector as components along I hat, j hat, k hat. I'm going to write any function in a particular space in terms of components of our orthogonal functions, f1, f2, f3, f4, and so on. What we will ultimately want to do is say, well, there's more than one set of basis unit vectors for vectors. I don't have to use Cartesian, I hat, j hat, k hat. I could use spherical. I could use r hat, theta hat, and phi hat. Well, the same thing's going to happen for our functions. We can find multiple different sets of basis functions to expand other functions in terms of. And so that's the direction that we're headed. Okay. Note that if I take the inner product of f with itself, that has to be a real result, because we're going to have f star times f, which is the absolute square of f. And that has to be a real number. So by definition, this is a real number. So the imaginary part's 0. Of course, it has to be, because the imaginary part was telling us about if it was 0, then our vectors are parallel. And f is certainly parallel to itself. So this involves only the dot product, or the square of the dot product, and that tells us the square of the length or the magnitude of f. So f inner product with itself is considered the magnitude of f, and that's because, oh, that's not good. I'm gonna lose battery. Does anybody happen to have a USB like plug adapter? No. Yeah. Oh, nice. I've got the power cord, but not the plug. All right. So. Okay. Yeah.
I do have a.
That's all right. We'll see. Maybe someone else has it. You do? Yeah, oh, nice, thank you. Thank you very much. Don't let me forget this, okay? I'm a forgetful person. Okay, perfect. Thank you very much. Okay, so the inner product of f with itself is defined to be this. You could see the absolute square, and so we're finding the magnitude of this function. So this must be real, and so therefore f inner product with itself is exactly like the dot product between vectors v dot v is equal to the square of the magnitude of v. But we do these kinds of calculations for wave functions all the time. It's our normalization condition. We require that some psi dot inner product with itself has to be equal to 1. Okay, so the normalization requirement for wave functions is psi inner product with itself is equal to 1 is like constructing unit vectors like I hat dot I hat is equal to 1. So if we find a set of functions that are orthogonal to one another, they're going to make a useful set of basis functions. If we then normalize them all independently, they're like a set of basis unit vectors, and we can write any other function in terms of that set. Okay, so if we find a set of mutually orthogonal functions that are individually normalized, we call them orthonormal. And we've seen examples of this already. We showed that the stationary states of the infinite square well were orthonormal, and we showed that the stationary states of the harmonic oscillator were orthonormal. We will fairly shortly, either today or next time, we are going to prove this generally for any set of particular set of wave functions for some operator, like a Hamiltonian or the time-independent Schrodinger equation. So, in essence, we're forming a set of unit vector-like functions, just like we can write any vector in terms of components aligned with a basis of unit vectors. So this is something we've seen many, many times. I could write any vector v as a component aligned with I hat, and another component aligned with j hat, and a third component aligned with, say, k hat. Where if I want to find the x component what I do is I take my vector expressed in any way you want, and I take a dot product with I hat. So I would say the x component is v dot I hat. The y component, vy, is v dot j hat, and vz is v dot k hat. So I want to do the same thing for my functions. Let me just think about the meaning of this. This is the projection of v onto I hat. So this is the projection of v onto I hat. What I want to do is I want to do this for my functions. So I want to say, I'm going to take some f of x that lives in some space. I suppose that I have a set of mutually orthogonal basis functions that span this space, just like I hat, j hat, and k hat span all of R3. And we will say my function could be some coefficient times my basis functions. So these are going to be like my basis functions. They're the analogies to the I hat, j hat, and k hat. And this coefficient has to represent my projection of f of x onto cn of x. And that projection is a dot product for our vectors. It's an inner product for our functions. So where cn is going to be, let's see, it is psi n inner product with f. And we've done this already when we were saying, given some initial wave function at some time t equals 0, it was some expansion of our stationary states, and our job was to find those coefficients, and we did exactly this kind of calculation. Okay, so we've already seen some examples of an orthonormal basis of functions. So one of them are the stationary states of the infinite square well. These were like our standing waves, our sinusoidal functions. And if you think about it, our sinusoidal functions like sine x, sine 2x, sine 3x, sine 4x, we already know that's a basis of functions because we already know the Fourier series expansion for periodic functions. I can write any periodic function on the domain 0 to t in terms of some superposition of these sinusoidal functions. And so that's exactly the kind of thing we're talking about. Another example that we've seen are the stationary states of the harmonic oscillator. In that case, our basis functions were kind of built out of these Hermite polynomials. And so we could write any function that exists in for our harmonic oscillator potential in terms of some expansion of these Hermite polynomials. Okay, good. So one issue that we have is that we're not guaranteed that an inner product between two arbitrary functions exists. So for example, if one of our functions diverges, goes to infinity, as x goes to infinity, for example, then there's no way that we're going to expect the inner product. which is like calculating the area beneath some product of functions, is going to be finite. So we have to restrict ourselves to the types of functions that we can work with. So one issue is that not all inner products converge. The normalization requirement psi inner product with itself is equal to 1. I mean, remember where this requirement came from. It came from our interpretation of the wave function, where we said the square of the wave function was going to be some probability of finding a particle between x and x plus dx. So if we integrate over all space, that probability better be 1. So there's really a strong physical motivation for this normalization requirement. But it restricts the possible psi of x to the set of all. So here's some terminology: square integrable complex functions. On a specified interval. So from, say, A to some B. That interval might be plus infinity or minus infinity to plus infinity, or it might be restricted, as in the finite square well, between 0 and A or whatever. So it depends on the potential, what your domain looks like. Okay, so our requirement is that in order for our functions to be normalizable, this inner product has to be finite. And then if it is finite, we could always scale it so that the inner product is equal to 1, or if it's a normalized wave function in that case, must be finite. Okay, so in technical terms, if f of x and g of x are both square integrable, or if you like, if they're both normalizable, then their inner product fg is guaranteed to exist. And we say that G and F are both in so-called Hilbert space. So we can think of this space as all square integrable functions, all normalizable functions on some specified domain that's going to be determined by the geometry of our potential. Okay, so we will spend a lot of time looking for orthonormal basis functions. So let's try to work out some of their properties before we go find some examples. So let's notice the following. If I was to take the inner product between f and g, that's just a shorthand notation for the integral of f star times g over x. Okay, Well, what would happen if I was to take the inner product returns some complex number, so I could take the complex conjugate if I wanted to. So if I take the conjugate of this inner product, it's the same thing as taking the conjugate of this entire integral. Okay. But the only complex quantities in here are f and g, so the conjugate of f star is f, and the conjugate of... Ooh, are we charging here? Oh, no, it doesn't say it's charging. Why is that? Yeah, is the desk plugged in? That's a good question. Oh, some kind person unplugged it. That's not the language I wanted to use. Okay, good. So we are charging now. All right, so when we take this conjugate, we're going to get the integral of f g star dx. But these are just some functions, so I can change their order. And so this is g star f dx. But that's exactly how we would define the inner product between g and f. And so this is equal to the inner product of g first and then f. And so notice that there's this relationship between the two. The order matters. If I switch the order, I have to take the complex conjugate, or I get the complex conjugate of the other result. And so the imaginary part is going to reverse sign in this case. Okay, so therefore, we are going to have f, g, inner product. If I take its conjugate, that's equal to the inner product between g and f. So that's a difference between, say, like a dot product. However, it's in some ways similar to the reason that we get the sign change is because the imaginary part is like the cross product, and the cross product between vectors, v1 cross v2, is minus v2 cross v1. And so that's the origin of the imaginary component changing sign. Okay, so the order of the inner product for complex functions matters. All right, so that's some preliminary things. I had a different kind of calculation right at the beginning. I had a calculation of an expectation value with some operator between the two functions in our inner product. And so what I'd like to do is I'd like to spend some time thinking about that. So we're in 3.2 of Griffiths, and we're going to talk about observables. So we know that the expectation value of an operator, q hat, is given by, okay, so expectation value of q is the integral of psi star. Then we act with our operator on psi and integrate over x. And so in our new notation, I'm going to write that as the inner product between psi and q acting on psi. Okay. Now, measurable quantities such as the expectation value of q. Remember, our kind of the way we think about this is we have some system that's prepared in a particular way. And then we imagine that we have an ensemble of copies. So they're exactly the same system, prepared in exactly the same way. We set them off, we let them go. But then at some time later, we measure the same quantity in every single one of these systems, and we get some distribution of values. The average of those values is the expectation value. That must be a real number. Okay, so this must be real. Okay, so that means that if I was to have the expectation value of Q, if I take its complex conjugate, nothing happens. A real number, if I take its complex conjugate, it doesn't change. All right. So that's kind of interesting because I know that the expectation value of Q I could write as psi Q hat times psi, right? It's right there. And so what we're saying is that is equal to psi Q hat psi conjugate. But we just argued that when I take the conjugate of an inner product, it reverses the order. Okay. So this has to be the same as Q hat psi acting on psi. All right. So one of our kind of funny results, which we're going to try to interpret right now, is this kind of odd looking expression. And so let's see if we can understand what this is really meaning. And we're going to try to do this again by thinking in terms of linear algebra. So this is true for any side. And I'm going to call this equation star because I'll refer to it later. This kind of relationship has a name. So operators of measurable quantities like momentum or position or energy, those are some common examples. Later in the term, we'll probably talk about angular momentum, things like that. So operators of measurable quantities must have this property, and this property has a name. So operators that obey equation star are called Hermitian operators. They are called Hermitian operators. Okay. Now, I know that this is some kind of abstract thing, so we're going to try to make it less abstract right now. And I think we have, what, 15 minutes? Okay. So let's interpret the meaning of star. Okay. If we think of our state, our wave function as a column vector, that's how we started the class. Oh, so yeah, I'm getting ahead of myself. Think of psi as a column vector. Then this weird looking thing, Q hat acting on psi, is another column vector. So if we think about how we transform vectors, if I have a column vector and I want to construct a new column vector, that's not just like a trivial scaling. Like I could just multiply it by a scalar and that just scales every component. That's not that interesting. But if I want to transform it in a more complex way, what I do is I multiply it by a matrix. So if I take a square matrix, multiply a column vector, I'll get a new column vector. So we're going to interpret this q hat as a square matrix. So I can transform a column vector to another by acting on it with a square matrix. So it was a few weeks ago, someone was asking, are we going to talk about the matrix representation of operators? The answer is yes, and of course that person's not here. Okay, so here's our column vector. And so it's going to have all these components up to psi n, let's say. And then I'm going to represent my operator as a square matrix. So it would have like a 1, 1 element, a 1, 2 element, up to a 1n. And then there's going to be the 2, 1 element. There's going to be the 2, 2 element. This is going to continue. This is going to go to qn1. We'll have qnn over here. And so there is my matrix representation of some operator. So then if I was to think about what we wrote down here, it's the product of this square matrix and our column vector. And I'm actually going to write out a bunch of the terms. So let's see, can I fit this on here? Sort of. All right, so I want to imagine this. Here, maybe I'll move it over there just temporarily so that we can do this calculation. Let's take a copy of this and let's temporarily paste it over here. All right, so what I'm going to do is I'm going to take this row, I'm going to multiply it by that column. And so I'm going to get, let's see, q11 psi 1 plus q12 psi 2 plus and so on. q1n psi n. So that's the first row of our new column vector. Then I'm going to take this one, that row, the second row, multiply it by that column. So it's going to be q21 psi 1 plus q22 psi 2 plus and so on plus q2n psi n. Okay, this is going to continue on. When we get to the last one, it'll be the bottom row, qn1 psi 1 plus qn2 psi 2 plus and so on plus qnn psi n. So that's our new column vector. All right, I'm going to call this equation 1. And we're going to apply the same sort of logic to this beast here. So remember, on the left-hand side of our inner product, we thought of a row. So a row is like a transpose of a column. Also, we had to conjugate all the elements. We took the complex conjugate of all the row matrix elements. And so what we're going to do is we're going to take our square matrix, we're going to take the transpose and the complex conjugate, and we're going to multiply our row vector by that. All right. So let's see if we can do that. So by the same logic, the left-hand side of our inner product is psi 1 star, psi 2 star, and goes on to psi n star. So this is the transpose and complex conjugate of the right-hand side of an inner product. All right, so that means if I wanted to think about Q times psi, we have to be a bit careful here. This is a 1 by n, 1 by n matrix. It's one row with n columns. So if I want to make another 1 by n structure, I have to multiply it by an n by n matrix. So my matrix multiplication is going to be on this side. So we're going to have psi 1 star, psi 2 star, so on, psi n star. And then trying to leave a bit of space, I'm going to put in my operator square matrix. And so let's see, Q11 star. And now I have to be careful because we had Q12, 13, 14, and so on, but I have to take the transpose. So those go along here. So my Q12 star goes here, and then I'm going to have Q1n star over here. And what I used to have here is a Q21, but I took a transpose, so that's over here. Q21 star, and so on, Qn1 star. And then Q22 is still here. Take the complex conjugate. Qnn is still there. Okay, so there we go. So this is my complex conjugate and transpose of this square matrix. All right, and so what I want to do then is I actually want to multiply this out. It's going to be a little messy, but that's okay. So in fact, what we're calculating is Q psi on the left-hand side of an inner product. All right, so now what we're going to do is we're going to take that row, multiply it by this column. And so what are we going to end up with? Psi 1 star Q11 star plus psi 2 star Q, it's 1, 2 star plus and so on, psi n star Q1n star. That's the first element. This is a little bit awkward because that's all one element. So I'm going to put a dashed red line here to indicate the start of the next element. And what are we going to do? We're going to do that row times the second column. So it's largely the same thing, except the first indice of Q goes from a 1 to a 2. So psi, it must be psi 2 star, Q22 star, plus and so on. Must be psi n star, Q n2, I think. No, it's Q2n. 2n. Yeah, so over here is 2n. All right, and then we'd have another element, and this is going to go on and on. So I want to call this equation 2. So can I get 1 and 2 on here? Sort of. All right. So what we're going to do is we're going to try to think about equations 1 and 2 and how they can be used to satisfy star. So let's start with equation 1 here. If I wanted to complete this inner product, what I would have to do is I'd have to take equation 1 and I'd have to multiply it by a row vector, the psi row vector. So psi 1 star, psi 2 star, psi 3 star, psi 4 star, and so on. And so if I did that, I'm going to get like psi1 multiplying all these things, and then psi2 multiplying all these things, psi n multiplying all of these things, and then we would just do all of those inner products that we have to do, are all those sums, the way we've written it as matrices. If I wanted to do the same thing for 2, I'd have to multiply by a column here. And I'd have psi1, psi2, psi3, psi4, psi5. And I'd get psi1 star times psi1, q1, 1 star. Psi1 times psi2 star, q1, 2 star. And what I would require is that those two products have to be equal by equation star. Now, what's the difference between equations 1 and equations 2? The only differences are that the q is the complex conjugate in equation 2, and it's not in equation 1. The other difference is the order of the indices that we're going to get. Okay, and so what I want to say is, considering 1 and 2, the only way that star, I'll rewrite star. So our equation 1 is this part. So the only way that we can force these things to be equal, equation 2 is this part. So the only way that star can be satisfied is if we say our original Q matrix, 2, 1, n1, here's 2, 2, here's n. This has to be equal to q1, 1 star, and now I have to take the transpose, q 2, 1. And this goes to qn1, q1, 2. And that's going to go to q1n. Here's q2, 2. And here's qnn. All right. So I'm going to require this to be equal if I want to satisfy this expression. So the transpose and the complex conjugate of some matrix representation of an operator has to leave that matrix unchanged. So specifically, that means these indices are reversed here, and we have a not conjugate and a conjugate here. All right, and so I think I'll write down a statement about this, and then we will be done for today. So in other words, in the matrix representation, operators representing observables must satisfy Q is equal to Q conjugate transpose. So this is complex conjugate plus transpose. So I think that's where I'll stop for today. This has a name. It's called the Hermitian conjugate. So when you read Hermitian conjugate, it means complex conjugate, then transpose. All right, so that's where I'm going to stop today. I'm going to stop this recording. Oh, no, we've got some people on there. So about the midterm, so you would prefer to write on Monday?
but I don't, it's not a strong paper.
It's not a strong, so you would be okay with, so if you have a change of heart, let me know. Any other objections to Monday? Everyone would be happy to write on Wednesday. Okay, so that's what we'll do. We'll write the midterm on Wednesday. And then if you are on, like, we can make some arrangement. You could write it on Monday outside of regular class. So that's up to you. So just let me know if that's something you want to consider. Okay, all right. So then we'll have a regular class on Monday, and then the midterm we'll write on Wednesday. Okay, all right. Thank you. Have a good few days.